Okay, so this is an explanation of why you should pay attention in math class if you want to be an amazing terrain maker when you grow up. So, I was working on a piece of terrain which was a cargo tube. There's like these little rings, and you put cargo in them, and the rings sort of like hover the cargo and run it along a track. So, the rings I wanted to be shaped like octagons, but I didn't want them to just be straight vertical octagons. Instead, what I wanted was slanted octagons. And then so I was building this out of foam core. So when you're building things out of foam core, you basically have to make a flat object and then decide how long everything's going to be and where your folds are going to be, and then you have to cut things and measure things and so on. And so trying to make an octagon that does this is actually fairly challenging. So my first attempt to do this was like this on the left side here. So keeping in mind that when I was building it, I was cutting it half on the bottom because my strip has to cut somewhere. So I did it up down there. So I have the bottom, and then the bottom right, and then the right, and then the top right, and then the top being a double width piece. Top left, left, bottom left, and bottom again. So the two bottom pieces link up down here at the bottom. And so on my first attempt, I didn't really think about it that hard, and I basically just said, okay, so this top part on this diagonal bit here is going to be flat, and this bit's going to be flat, and I'll just draw a straight line. But if you just draw a straight line between there and fold it up as an octagon, you're going to have this when you look at it from the side. Essentially, it's going to, on the part that's flat here, it's going to be a steep angle, and on these ones going to be a shallow angle. And you get sort of like an S shape instead of having a clean perceptual line. So the reason for that is that in an octagon, when you're looking at edge on, you will have, even though in mine I had basically all of these faces are 1 inch, you're looking at this face and this face from an angle. So they're not rising up as high as the one that is using its entire length to rise up. So here you're actually only seeing part of this used to rise up. And so since it's not rising as much, but I was still having it with this one, I was still having it go forward as much as the one that was straight up. So visually, this one is going forward too fast, and then it gets to here and it goes forward less as a function of how much it's rising, and then here it goes forward too fast again. So in order to actually make this work, you need to end up with something more like this, which is where on the top it's flat and on the bottom it's flat, and on the left it's the full angle, but then on these diagonal pieces, it has to be shallower. It has to go forward less, so less transition horizontally, because they're not rising as much from the visual. Because I think we're just doing a perceptual straight line. So the question then becomes, well, how much are they rising? And this is where you need to pay attention in math class. So I believe this is grade 10 math in here in Canada, or it was when I was in high school. So this is the unit circle, and this is basically introduction to trigonometry. So the unit circle basically says you have the 0 point here, you have 1 on the x, minus 1 on the x, 1 on the y, minus 1 on the y, and it basically says that if you have some sort of angle and it goes from the origin, an angle that takes you to any point on the unit circle, how far along are you on the x when you hit that point on the unit circle, and how high up on the y are you on that point in the unit circle. And that's where sines and cosines come in, because the sine is how high you are when you impact the edge of the unit circle. Cosine is how far you are along on the x. Fortunately, I was building an octagon that used 45-degree angles, and the sine and cosine are going to be the same. Specifically, root 2 over 2 is what both of those values are, which equates roughly to 0.52532198881. So this value is the percentage of the rise that these ones will look like they're rising up. When I was building my piece of terrain, every one of these segments is 1 inch. That means that visually, perceptually, the slanted part here and the slanted part here both rise up visually 0.5253 inches. So then we can use that information to determine how to actually draw this curve. So to do that, I draw my shape, and then I say that this segment here is going to have a y component of 1, and then these ones are going to have a y component of 0.525, and same thing down here. And then we have to figure out what is the angle that the flat piece is going to be. The top and the bottom are going to have no angle, they're just going to be a straight line. And the one on the side here is going to be what I'll call the full visual angle. So when you're looking at it from the side, whatever angle this side piece is here is the one we need to essentially mimic with these. So I didn't actually use an angle, I used something I could do with a ruler. So basically I had it rise up 1 inch and then go over 1/2 inch. So since this is going over 1/2 inch, this one is only rising up 0.525 0.525 times the height, so it also needs to run the 0.525 times the 0.5 inches, which in this case becomes 0.263, right? And that's how far these will travel along. All of which brings us back to this shape here, and that's where we end up with, over the course of these all being an inch, this one is going to drop down 0.263 inches, and then on the next 1 inch segment, it's going to drop down a full 0.5 inches, and then on the last one, it's going to go down another 0.263. And basically, that's where I ended up with this, which I did on a computer in Illustrator. So I had Illustrator build me like mathematically accurate squares that were 0.263, and then this one is 0.263 plus 0.5, and then this one is 0.263 plus 0.5 plus 0.263. And then I just put a vertex at the corner of each box, and then that is where I ended up with my awesome Spud wave. So it goes wah, like that. And then so if you trace this out on a piece of foam core and you curl it up and make it into an octagon the way I did here, and then you look at it from the side, you get a perceptual continuous angle. So yeah, that's basically where we end up, is I've got this cool wave, and that will give you a slanty octagon. And so if you have your own terrain stuff that you want to make, you can use math to make your terrain more awesome, the way I made my terrain more awesome. Because look how awesome this looks. It looks so awesome.